Welcome to lecture 4. In this first week of optimization in chemical engineering course, we are talking about introduction to optimization. So, after giving you a brief introduction to optimization and after talking about problem statement, classification of optimization problems and after giving few examples on engineering applications of optimizations, in today's class and in the next class, we will briefly review linear algebra that may be required for our course. So, today we will start our review on linear algebra. So, during our discussion on review on linear algebra, we will essentially talk about vectors and matrices. So, today we will talk about vectors and various vector operations. Vector is a directed line segment in n dimensions. It has both length and direction. Vector in n dimensional real space is an ordered set of n real numbers. So, an n dimensional real space is shown like this, r to the power n. So, V equal to 1634 is a vector in 4 dimensional real space. Why? Because it has 4 number of elements. The column vector is written like this, whereas row vector is written like this. You know the transpose of the column vector will be a row vector. A vector is also represented like this. Vector addition and vector subtraction. So, if you have a vector with elements u1 and u2, you have another vectors elements v1 and v2, the addition of vectors will be u1 plus v1 as first element and u2 plus v2 as second element. So, both the vectors have same number of elements. So, you can perform vector addition. Similarly, vector subtraction, you will subtract elements of first vector and elements of second vector. So, u1 minus v1 will be the first element, u2 minus v2 will be the second element. The difference of two vectors is the result of adding a negative vector. So, it can be written as a minus b equal to a plus minus of b. Here are some properties of vector addition. Vector addition follows commutative property. So, a plus b equal to b plus a. It follows associative law. So, if you perform a plus b first and then add c to it, the result will be same as if you perform b plus c and then add a to it. There is a 0 vector for which all the elements are 0. So, if I add a 0 vector to another vector a, the result will be a. So, a plus 0 equal to 0 plus a equal to a. Note these properties. b plus a minus b equal to a, minus of minus b equal to b, minus of a minus b equal to b minus a. So, vector follows these rules. What happens if I multiply a vector by a scalar? Consider V a vector which has elements, let us say x1 and x2. You multiply the vector, let us say by a scalar alpha. What happens is each element of the vector gets multiplied by alpha. So, the direction of the vector remains same, but its magnitude changes. Magnitude becomes alpha times the vector. So, it becomes scaling. So, vector multiplication by scalar follows distributive property. So, alpha into a plus b is alpha a plus alpha b, alpha plus beta into a equal to alpha a plus beta b, where both alpha and beta are scalars. Vector multiplication by scalar also follows associative rule. So, alpha into beta plus into a is alpha beta into a. If you take scalars 1, alpha, 0 or minus 1, they will satisfy 1 into a equal to a, alpha into 0 equal to 0, 0 into alpha equal to 0, minus 1 into a equal to minus a. What do you understand by linear combination of vectors? Let us consider vectors v1, v2, v3, v4 up to vn in n dimensional real space, and also consider n real numbers as C1, C2, C3, C4, C5 up to Cn. So, the vector that I obtain by linear combination of v1, v2, v3, v4, vn is called a linear combination of vectors v1, v2, v3 up to vn. That means, the vector x obtained as C1 into v1 plus C2 into v2 plus C3 into v3 up to Cn into Vn is called a linear combination of vectors v1, v2, v3 up to Vn. Examples of linear combinations of v1 and v2 may be 0.5 v1 plus say square root 5 v2, 0.5 v2 equal to 0 into v1 plus 0.5 into v2. Linear independence of vectors. This is important. We need to understand what we mean by linearly independent vectors. A set of vectors v1, v2 up to vk is called linearly dependent if there exists scalars c1, c2 up to ck, not all 0, such that c1 v1 plus c2 v2 up to ck vk equal to 0. So, if you have vectors V1, V2 up to Vk, and there exist scalars C1, C2 up to Ck which are not all zeros, then if Ci Vi equal to 0, meaning C1 V1 plus C2 V2 up to Ck Vk equal to 0, then the set of vectors V1 V2 up to Vk is called linearly dependent. The vectors V1 V2 up to Vk will be linearly independent if sigma Ci Vi equal to 0 or C1 V1 plus C2 V2 up to Ck Vk equal to 0 only when C1 C2 all Ck equal to 0. So, for vectors that are linearly independent, sigma Ci Vi equal to 0 only when C1 C2 up to Ck equal to 0. So, here are some examples of linearly dependent vectors. Consider I have a set of vector 1, 2 and 3, 4. So, you have 1, 2, you have 3, 4. The question is, are these vectors linearly dependent or independent? They are linearly dependent because if we do this, that means if I consider C1 as minus 2 and C2 as 1 and take the sum C1 V1 plus C2 V2, I get 0. Why? So, this is minus 2 this is 2 4. So, minus 2 plus 2 minus 4 plus 4 equal to 0 0. Similarly, the vectors 1 0 0 1 minus 2 5 is also linearly dependent, because you can also show that 2 1 0 plus minus 5 0 1 plus 1 minus 2 5 equal to 2 minus 2 minus 0 minus 2 0 minus 5 plus 5 equal to 0 0. So, this set of vectors are also linearly dependent. Now, let us consider another example. You have the following set of vectors V1 equal to 1 2 3, V2 equal to 0 1 2 and V3 equal to minus 2 0 1. Are these vectors linearly dependent or linearly independent? Let us follow the same procedure. If the set of vectors are linearly independent, so the sum C1 V1 plus C2 V2 plus C3 V3 will be equal to 0 only when C1 equal to 0, C2 equal to 0 and C3 equal to 0. So, let us get the sum C1 1, 2, 3 plus C 2 0, 1 and 2 plus C 3 minus 2, 0 and 1. So, this will be equal to 0. So, do the sum, which will be C 1 plus 0 minus 2 C 3, 2 C 1 plus C 2 plus 0, 3 C 1 plus 2 C 2 plus C 3 equal to 0, 0 and 0. So, this is also 0, 0 and 0. So, basically you have 3 equations, C 1 minus 2 C 3 equal to 0, 2 C 1 plus C 2 equal to 0, 3 C 1 plus 2 C 2 plus C 3 equal to 0. So, you have 3 equations in C 1, C 2 and C 3. You can solve these 3 equations and find the values of C 1, C 2 and C 3. You will see that the values are coming as C 1 equal to 0, C 2 equal to 0 and C 3 equal to 0. That means, this set of vectors are linearly independent. So, that is why you can see here. A set of vectors is linearly dependent if and only if one of the vectors is a linear combination of the others. So, we are talking about some properties of linear independence. A set of vectors is linearly dependent if and only if one of the vectors is a linear combination of the others. Any set of vectors containing the 0 vector is linearly dependent. So, any set of vectors containing the 0 vector is linearly dependent. If a set of vectors is linearly independent, then any subset of these vectors is also linearly independent. So, if a set of vectors is linearly independent, then any subset of these vectors is also linearly independent. If a set of vectors is linearly dependent, then any larger set containing this set is also linearly dependent. I repeat, if a set of vectors is linearly dependent, then any larger set containing this set is also linearly dependent. Now, let us talk about dot product of vectors. The dot product of vectors are also known as inner product or scalar product. You can consider this dot product as something similar to matrix multiplication. So, the dot product between two vectors A and B, which is also represented as A transpose B, is the product like this. So, A, B, C, A and B are both column vectors. You have taken A transpose B. So, A becomes row vector and B becomes column vector. So, if I say in terms of matrix notation, this is 1 row 3 column, this is 3 rows 1 column. So, the multiplication is defined because column of the first matrix A is equal to rows of second matrix B. You also can immediately see then the product will have dimension 1 by 1, that means it is going to be a scalar. So, the dot product is a scalar quantity. So, if the elements of matrix A is A, B, C and the elements of matrix B are D, E, F. So, the dot product between A and B is AD plus BE plus CF, which is a scalar quantity. So, the dot product is also represented like this. Two vectors x and y, the dot product is sigma xi yi for all values of I equal to 1 to n, where n are the number of components in vectors x and y. The magnitude of a vector is the dot product of a vector with itself. So, A transpose A. If A has elements A, B and C, A transpose A becomes AA plus BB plus CC. This becomes the magnitude of the vector A. The dot product is related to the angle between the two vectors. So, two vectors A and B, the dot product between two vectors A and B can be written as A to B into cos theta, where theta is the angle between these two vectors A and B. Corresponding to inner product, we have also another term called outer product. So, the inner product or the dot product between u and v, let us say I have two vectors u and v, and the elements of u vector is u1 and u2, and the elements of v vector is v1 and v2. So, the inner product or the dot product between u and v is u dot v equal to u transpose v is u1 v1 plus u2 v2. But the outer product between u and v is u v transpose, u v transpose. Inner product is u transpose v, outer product is u v transpose. So, u and v are both column vectors. So, u is column vectors. Now, v transpose, that becomes a row vector. So, u1 u2 v1 v2, u1 e2 is a column vector. So, you have 2 rows 1 column. v1 v2 now has become row vector after taking transpose, and it has 1 row 2 column. So, the matrix multiplication is defined and the product is going to be 2 by 2 matrix. So, this is what you get u1 v1, u1 v2 elements of first row, u2 v1, u2 v2 are the elements of second row. Vector norms. The norm of a vector is a measure of the magnitude or length of the vector. There are different types of norms. Common norms are 1 norm, 2 norm or infinity norm. 1 norm is defined as this. So, you sum up the absolute values of all the elements in the vector. 2 norm is defined like this. You square all the elements in the vector, sum them up and take the square root. Infinity norms is defined as this, where you take the maximum value of the elements in the vector. So, in general, the P norm is defined as this. Look at the similarity between the 2 norm and the p norm. So, put p equal to 2, it becomes 2 norms. So, mod x to the power p, sum them up and then raised to the power 1 by p. Here are some properties of vector norms. The norm of a vector is greater than 0 if x is not equal to 0. So, if x is not equal to 0, the norm of a vector which represents the length or magnitude of the vector is always greater than 0. Consider vector x, consider a scalar alpha. So, the norm of alpha x is equal to absolute value of alpha into norm of x. And finally, norm of sum of two vectors is less than sum of norm of those two vectors. This is known as triangle inequality. So, if you consider vector x, if you consider vector y, you sum the vector x plus y, take the norm of x plus y, that will be less or equal to sum of norm of x plus norm of y. So, that is known as norm of triangle inequality. With this, we stop our lecture 4 here.